All right. Yeah. Okay. So this is kind of an overview on the Air tool chain flow that AMD has that's situated above their AIE tool chain. So this is to my best understanding of how their tool flow works. Um, so just for a very short background knowledge, this tool is also built out of MLIR, which is multi-level intermediate representation. Kind of why this tool gained popularity is that you want to have kind of a reusable compiler framework. The idea is that people make their very own customized ones, and this becomes a problem when you're trying to scale up this maybe across a big kind of one big issue is that when you have different devices, this becomes a headache. And the other reality is that certain optimizations just work better when you have a different level of abstraction to it. But then the problem is like, how do you then do a common lowering or kind of a gathering of the different abstractions that you've made previously? So Amara kind of aims to make it really cheap to define a new abstraction. So they provide a lot of in the box tools. So like the very most basic kind of example is like you once you had to clear a dialog, you have like a built-in print, like that as a very basic example. So why the air tool really exists is that accelerators are fast because they try to separate out your data flow from computation. So this allows for you can interleave those operations. You don't want anything that's kind of like from a let's say from a CPU, you would have kind of any sort of stalling when you're fetching from memory. So, but also from like a user perspective, you how AIE works is that you're kind of made to write two separate files. You have one that defines all the computations for the hardware, but then you have that separate control flow. So for a user programming, this is probably a kind of a annoyance, and the other reality is the expectations from stuff like CUDA being the most popular library. You kind of have like that unified location where you can write out your host testing as well as setting up the kernels themselves. So having a nice single source language that sits above that needs to actually capture both both of these data flow and the computation. And the other reality is that higher level applications aren't going to be separating these. When you have your PyTorches, that they don't care about that data, especially data flow. Yeah,
This is a good question. So, just so I understand what you're talking about, the host.cpp, that's basically what's running on the CPU, and
yeah,
that's kind of orchestrating everything.
yeah,
And design.mlir, that's what's going to go on the accelerator. So it's
yeah,
like a set of instructions the accelerator is going to perform
yeah,
when the host says to do something.
yeah, exactly.
And what you're arguing for here is that instead of having two, the host.cpp and design.mlir, you want to combine them into one so you have a heterogeneous compiler toolchain. Or
Yeah,
they're both heterogeneous, but a single source file as the input.
yeah,
I see.
and if you were to, let's say, you have two ways. Either you're programming at this level or you take from another higher level application.
I
So
see.
once you move upwards, this like separation they definitely doesn't exist.
Mhm.
So yeah, so their kind of their philosophy with the air tools that they wanted to target kind of their whole product line. Uh, so you can see that they have the AMD GPUs as well as the PL, which is the I guess it would be like more of the versatile type architectures. Uh, they're not quite there yet, but I'm assuming that's kind of their design goal when they started out. So
I'm gonna stare at this for a second. Yeah, I'm
yeah,
also curious this image. Where did you get this image from?
so this is from their previous Air presentation, which they haven't had one in for the past years.
It's a good picture. I'm surprised they're also targeting circuit, CIRCT.
Yeah, that one's also another MLIR built kind of, I guess, still considered compiler.
Yeah, it's an MLIR toolchain flow targeting FPGAs. So it's like high level synthesis. I've heard of it. Where's it from? It's an open source effort. I don't know who owns it,
Hmm.
but I've been see they have a paper in the works that they've been working on for like the last year.
Yeah. So I think like a conclusion from this image is that when you look at the abstractions that they're making for MLIR, especially for hierarchies of representations they have, let's say for like a what they consider a kernel or something, keep in mind that they don't want to really say that it is a AIE core, for example.
Right.
Uh, yeah, they're trying to keep it general. Uh, but the real implementation, you'll see that it's pretty much still centered around
Another question I
AIs.
have
Yeah.
is I noticed a path diverging right before MLIR-AIR.
Yeah.
And so that's going towards the CPU. Is that the host code or is that something else?
I think what they're trying to say is that that's that let's say for like a PyTorch tool, like you
Oh,
could technically they already have backends that go to CPU, so that
so
just
that's
has
not a two split. That's like
yeah.
go this way or go that way.
I think that's how I understand it, because the host program does come out of Air,
I see.
right? So
Is AMD still using ROCm as their GPU programming layer?
I think so. I was talking to Hung a bit about this
That's what they're using
recently.
still. They've gone through a few variations of their GPU ones. That's why I ask. So
Yeah, and uh, I'm assuming there is some sort of open source tool uh, to accept MLIR, but I think I'm assuming they can really do right now is just say they have like this unified dialect that may or may not be able to be passed to GB at some point in the
yeah,
future.
like some of
Yeah,
those might be aspirational arrows. Like in
yeah,
theory, I could go from here to there, but in practice,
yeah,
maybe no one's actually debunked it. So
yeah. So yeah, this is just the image from the AIE talk they had. So you can see that there is that test.cpp is the host code that stays on the CPU. It kind of tells uh when to activate which AIE core, for example, and yeah, and that one's also the one kind of managing scheduling pretty much. Uh, so yeah, this is just to show that there is that separation. And so also from that talk, in terms of refreshing, you have for AIE, the main idea is having a hierarchy where you have local L1 memories that are placed at the tile, and you have the L2 memories that are meant to be shared. Let's say for main goal is to share across AIEs that are probably doing the same computation tasks, and then the L3 being the off memory uh, DDR, for example. So for air, the way they try to map some any sort of application or computation is that they try to transform it into this this similar hierarchy. So I guess you can say that they're trying to match it to this architecture. That's how it's efficient. So yeah, so it's this high overview. If we start with like a high level implementation that's probably done in one of the dialects, which is Lineage, uh, we have like a just a basic matrix multiplication that we're doing. And what the air pool will try to do is we want to take this and then first match it to the air abstraction. So think of that hierarchy. So they have a kind of equivalent inside air. And the way to match that is using tiling. So tiling is when it works for regular patterns like a matrix multiplication where you're breaking that up into nested loops, and you make sure that whenever you have like an independent data access, you can parallelize that. Um, uh, yeah, and the other thing is when you have a higher level application, usually that data movement is not explicit, so you need to pretty much like parse that out. You want to transform that into something that is explicitly communicating, oh, which ones are the source and sink, who's trying to communicate. For hoisting invariant data movement, what that means is that we're trying to improve that memory transfer. What you can do is that you pull any sort of memory access out of loops. You can think of it as like it's like prefetching these memories. You don't want to be constantly accessing one, let's say like one bit within that for loop. You can probably just grab the entire channel of data or something ahead of time. And yeah, so and then the main goal is obviously separating the so that yeah, that's what is separating the data preparation from the computation. And then the output is something that is a bit blurry because AIR and AIE are pretty tightly integrated together. But what we should be seeing is like some sort of placed data graph that, or something like a almost like a netlist in FPGAs. Uh, yeah,
I just had a quick question.
yeah,
So I think I asked this the other day. So I see a lineage matmul on percent sign A and percent sign B.
yeah,
And what that means is that we have two input things coming in and producing an output.
yeah.
Are those memrefs or are they tensors in MLIR? Because a
Yes.
memref is an actual buffer of memory. You can think of it like a pointer, kind of, with a shape.
Yeah.
Whereas a tensor is like a immutable vector. You can only read from it. You can only create it. You can only read from it. You can't really write to it, I think.
So what they have at this level is that they start with the memref.
Interesting.
So and then I think buffering is done at some point in AIE.
I see.
Yeah. So here, yeah, here we just assume that they have these memrefs.
Hmm.
Um,
How well do people know MLIR? Do you want like more discussion of things like that or less or what?
I'm interested in it. I just don't really know MLIR.
Maybe one, I think I understand the syntax, but maybe just that line you have of MLIR syntax. On the
Yeah,
first one.
sure.
Why don't you just walk through what does that mean?
yeah. So for I think a easy way to think of it is the you have it's almost like a function declaration where uh the within brackets, yeah, those are the inputs, and then
So variables always start with percent, right?
yeah,
And it's single static assignment, so
yeah,
you're
just like
only
yeah,
ever write to a variable once,
yeah.
right?
So here we're pretty much saying that percent %C will it kind of identifies like what the output will look like, and then you assign it to the out variable at the very end.
The reason why I'm confused by that is
Yeah.
you're assigning to a memref.
Okay, so we've got lineage multiple, so okay, that's the operator, right?
Mhm.
Like the equivalent of an instruction. You got A and B are inputs. Actually, what is that just means this literally those are my inputs and my output is C.
Yeah, so that's I think that's just like Lineage's way of
Yeah, okay.
writing
Actually, I
it.
haven't seen that part
Yeah,
before.
It's annoying.
So
So
lineage just defined that they put this ins and outs on things.
yeah, they were the ones that started doing that. What they're doing here is the outs, you need to specify the shape of the output, and that might be it's basically their way of getting around when I lower my lineage to from tensors to memrefs, I need to know what type of buffer it should be put into. And if you put a tensor empty as your output, you're basically saying my output is this allocated memref. And lineage also works with memrefs. So generally speaking, if that were memrefs, I wouldn't see an equal sign. It would say lineage matmul ins percent sign A, percent sign B, outs, and then percent sign C would be the memref buffer you want to put it into. It allows you to do
So those can be
in-place.
memrefs. So why do I have a percent out on there as well?
I'm not sure. I'm double checking that now.
Yeah. All right, maybe it's too detailed. So
Yeah. I personally
So I have a question.
yeah.
Uh, so James, can you like I think from this slide I understand the input and I understand the output, but can you kind of like take this lin algebra example through the steps that you mentioned, just to get a better sense of what you mean by that?
Uh, Yeah, or I guess the next slides will like kind of transform this example down.
Mhm.
Yeah.
Just curious, that
Yeah.
green line of code, did you take that from the Airflow or is that something you
No, this is just like a generic like
Gotcha.
expression. Yeah.
Mm.
So yeah, uh,
Okay.
I'm not too familiar with like exactly how lineage's syntax
Mhm.
works. So
Because there is like in MLIR, you'll also have types in there, which make it a
yeah.
lot harder to
So
read.
I think this one's more clear on like what a
Sure.
really
Mhm.
more pseudo, still pseudo code version. I had to pull out a lot of details
Mhm.
from it. So what we have here is that first step of like tiling is you can say that they rely on using between lineage and SCF, which are built into MLIR at this point. So
So
you have
just a
that.
question, what's SCF?
I don't know exactly what it stands
Synchronous
for.
control flow, or what is it?
Standard.
Standard control flow?
Yeah, it's standard, I think.
I think it's
Ooh.
structure. Yeah.
So some history on this. It used to be called standard. Really? No. Yeah, structure. I'm wrong. It stands for structured control flow.
Okay.
Yeah. So SCF is good for representing usually loops. So
Mm.
that is what we're trying to do with it. So with the if you want to like lay out, let's say matrix multiplication, the best way is you break up the output into blocks and then you do so with the inputs as well. So for you can see that there the tool tries to split that into like a triple nested loop to match with the hierarchy that with the L1 to L3 hierarchy that we mentioned before. So the numbers kind of just they just work out this way. If you have 256 by 256, you break that up into 64, which would be I guess total of 16 chunks. Yeah. And then for the for loop inside is that reduction dimension, which means that when you have m by k mammal with k by n, you then need to break up the inner k so that it matches. And like on the very at the very center, you'll see that the actual mammal operation will be nested in that final the innermost loop. So yeah, parallel pretty much uh says pretty much it indicates that these can be independent from each other, whereas a for loop is sequential. So and then you'll also see that they've inserted this DMAM copy uh attribute or I guess operation. This is what replaces that memref from earlier. So this is just like a some internal type that they use as an initial representation, uh, and then later we'll show like that they do like further transformations for it.
So which type are you talking about?
This is
What type?
the red air dot.
Is it an op or is it a type?
It's a operation, but you can think of it as just a transfer.
But does it take any inputs or outputs?
So it does. I
Okay.
pulled those out because it is very confusing.
And then my
Yeah.
question might be a bit hard.
Mm.
I'm just really curious on this. Do they use address spaces to represent if something's in the L1, L2, or L3? Or do you know?
Um, so I'm assuming not with addresses. I think it's sort of determined by the where it is at the nesting,
That's
like
so
what
interesting.
level of nesting.
Gotcha.
Yeah. And yeah, I guess that's it.
I guess the DMA mem copy, when they get low, it would turn it into. Hmm.
Yeah, so then we actually are matching these to the air definitions. So it's kind of the optimization tiling that they do is such that you can have kind of this exact matching. So I guess like one caveat that comes up is that your operation has to be some sort of regular pattern where you can do this tiling, otherwise it wouldn't work. So for the inner part,
Can you walk me through like, okay, so the
Yeah.
innermost loop is an SCF4. Okay, so that's not parallel, you're saying.
Yeah.
It goes from 0 to 256, and the colon 32 means
It's 32's step of 32's.
the step of 32. So that's just the step. Is that right?
Yeah.
Let me think about that.
And
How does that step work? Is it like a tiling pattern, or is it literally just incrementing by 32? What does it mean?
So you can think of it as like within each 32, they'll do like a sequential I guess it'd be like one operation that they're doing. So the matmul inside will be like some stat like 32
So
at
like
once.
32 elements.
Yeah,
and
or
so
like
that 32 really means like increment the index by 32.
yeah, so
That's what it means?
it's
Okay.
like it's for like it's like saying for compiling and like it's like C code almost where you need to let it know that you need the next loop you want to
So this
jump
will be like
to
a
30.
for loop in C from like 0, I equals 0, I less than 256, I plus equals 32. Is it like
Yeah.
identically equal to that? Like that's all it means?
Yeah, like
Okay.
more or less, yeah.
And then they're using SCF parallel. They're not actually going to be computing this in parallel. They're just saying that everything inside is independent of the previous and next iteration.
Yeah.
And that allows them to launch them in parallel.
Yeah. So
That's
parallel is
cool.
a good way to they're basically relying on SCF's ability to tell if something's parallel and they'll use that exact
This is actually a pretty common thing in MLIR. SCF parallel in the context of a CPU means running things in parallel, but in the context of a hardware accelerator, it just means that these things are going to be executed in parallel, whatever that means in your context. That's cool.
yeah. So I think this slide
James, sorry,
yeah.
can you go
Yeah.
back to the example? Like I'm still trying to wrap my head around it. Seems like this is like the simplest operation that you can do, but it's still
I'm wrapping
complicated.
my head around it too.
If
Yeah,
oh yeah, go ahead, Andrew. Sorry.
so I guess like this inner SCF dot 4, right? I
Yeah.
assume when you say actual matmul operation, this would be like a vector dot product, basically,
Yeah. Yeah.
for two vectors that are of size 32, and that's why you're jumping by 32 for those
Yes. Yeah.
indices, right?
Yeah.
And there's this air dot DMA mem copy underscore ND. What
So
is that?
so um I've removed a lot, but like that's supposed to just represent that you need to pull at or at least access somewhere where that the actual data is.
Okay, so
And
I'm bringing in two vectors, let's say two 32 element vectors from
yeah.
somewhere in the memory hierarchy.
Can I ask you a question though? I don't think. Let me think about that.
I also don't think they're
well, they're not. I mean, in the end, that's looping over 256 elements, but it's looping over them in groups of 32. So I think what's not shown is that actual mat multi operation is operating on 32 elements at a time. I think.
Right.
But I think that this, I mean, for this to make sense as a matmul, I think it has to be a vector of like 256 that's being dot producted, one row times one column. So I'm guessing that for loop is saying go through 32 elements at a time, but cover all 256. But what's underneath and not shown is some kind of vector instruction or some vector hardware thing, I think. This is a guess. That's doing 32 at a time.
My guess actually is from what I remember about how linalg gets tiled, they're just calling linalg.tile, and the tile pattern for matmul is known, and they're tiling it by 64 by 32. The innermost will be a matmul operation of, I think it will be 4 by 2 matrices. So 4 by 2 times 2 by 4.
Well,
No, that can't be right.
I think you might be off on a level.
I think I'm
It's
off on
like,
something.
Well, I don't. I think I'm at a level where I'm just trying to do this.
I'm just trying to.
Well,
So you're saying that
more. I don't know if that's
Sorry about that.
you're
maybe
saying
that's
that this 32 number is not related to the architectural parameter of like the
No, that's
vector lanes.
no, like the 32 is like just the like it's part of the a pass argument where I say like I want to keep however much on a core. Like if they've like completely like to the most lower level.
Mhm.
Yeah, so that is like it's the way that you invoke the tiling is that you say uh yeah, like how what I want the eventual like size splitting to be. So uh I guess the exact like how it has split isn't necessarily because it's like exactly what the hardware size is.
I see. So if we basically take the same approach on like from top to bottom, right? So I have two matrices. I tile each matrix into 4 by 4 tiles of 64 by 64 each, right?
Yeah.
And then I take each one of those tiles, tile them into 2 by 2 tiles again, right? And then this intermediate for loop basically has an increment that is equal to the range of the for loop. This means this is a single tile.
Yeah, yeah. So yeah, each one would be one of the 16. I can't work the math.
Yeah, I guess by the second line we are down to tiles that are 32 by 32 small matrices, right? So what I don't get is like, how did we get back to 256 by 256, right? And then we increment that by 32.
You know, 16 tiles in the second matrix. So you have 16 by 16, you know, smaller matrix multiplication.
Yeah, I think that's right.
So each of them is actually, you know, a tile by tile matrix multiplication. That's really 256 of fun.
And that's why you call it a reduction for loop, because you're reducing along those dimensions.
See.
I don't know.
Okay, so you're saying this like third for loop is actually looping over the tiles, the small tiles.
Tile pair.
Is looping over the tiles?
Tile pairs. For example, you take one tile from here, one tile from there. You have two matrices of same size. You divided each one to 16 tiles. You take from one from here, another one from here, and multiply them together.
Okay, so that's 4 by 4.
Two.
How do I get 16 by 16 tiles?
So the first tiling
Is 4 by 4.
you have a 4 by 4 tile.
Yeah.
You divide each one to 4 additional tiles, so you have 16 tiles.
Oh, right. Yeah, I'm not doing it in the other dimension, right? Okay, yeah, that's right. 4 by 4 is 16, makes sense. Okay. I have to go look up the detailed syntax of it, because the first two are like defining a tiling pattern, right?
Yeah, it is defining a tiling pattern. I'm just trying to figure out what the tiling pattern is. I think it's the inverse. I'm so lost. But anyways.
Okay.
Yeah, I guess yeah, the exact operation probably not don't have to worry too much because at some point this becomes pretty unreadable anyways. Like for example, like that for loop, they actually at some point the optimization breaks that into like at least like 10 nested for loops too, which I didn't show. It just becomes way too complicated. But yeah, it's mostly for like kind of definitions. It goes to just this is like kind of how they wrote it. It's kind of like a one-to-one design choice. So you have the Earthon launch, which is kind of like CUDA's grid, and that just means like you start a kind of like a parallel process. So I think yeah, so this is like this is how like GPU kerneling works. So beneath the hierarchy below launches, you have segments. So that means a partition of program uh, that's running the. I guess it's like a. Let me find the exact word that they use. So yeah, so for GPU, it's called like a warp. It's basically saying like you have uh or sorry, it's a thread block, which means that you can launch multiple processes uh that are probably doing different things, but these can still be in parallel. They'll probably occupy different resources. And believe that you have herds, which are basically warps. So this is similar to having you can have this can be a group of cores, but they're always operating on the same instructions. So you can think that they're working on the same thread. And the actual execute would be like an individual core. Um, yeah, and then yeah, so for compared to like a AI like for the AIE architecture, what you'll have is that you're placing herds onto the actual tiles. So this herd can span across multiple tiles, but they they are guaranteed that they have some sort of data communication between them. And see what else I have written. Yeah, and then the other kind of equivalent way of thinking is that like a launch will within a launch they would be working with that same L3 memory, uh, but then within the segment they're probably spawning from that one L2 memory level, and then for herd it's technically multiple L1s placed on their own tiles. Yeah,
Let me see if I understand this correctly, just from the full picture. I have a mapmul operation right now. That's
yeah,
all you told me. I'm now going to partition that mapmul into pieces. Each piece I can somehow guarantee will fit into the L3 memory. And then what I'm saying is then I'm going to partition it further so then it can go into the L2 memory. And then when do the AIE blocks come in? What do they compute?
yeah. So in for this example, it's you just have one launch in one segment,
Hmm.
and there's also technically only one herd because they're all the cores will be doing the exact same instruction, which is that matmul,
Okay,
right? So
that smaller mapmul, not the big mapmul.
yeah, sorry, the smaller matmuls.
Hmm.
So yeah, and then you can have yeah, the executes would be the individual cores actually launching the computation. Yeah. So I guess this example is not very telling of like a larger scale one. So there's only a single launch, a single segment, a single herd.
Hmm.
So kind of another flow is or another step is changing that DMA memcopy. Like they check for uh the source and sink and they transform it into air.channel. So this is now a AIE specific operation. So for channels, if you remember from that AMD talk, they have the object FIFOs. So object FIFO, it's basically equivalent to the object FIFO where you're saying that I don't care exactly how you're going to route this. I don't care what kind of medium you're going to use. All this channel will it has like an input, like a source and then a sink. So it just tells the yeah the entry and exit of this data transfer. Uh, the kind of other optimization is just to you detect for data broadcasts, and you can do this by looking at if you have the same source for a lot of memory transfers. And this is just for down the line, you can reduce the number of channels you're using for that source tile. So AIE has something that I guess kind of gathers up these broadcast routing and yeah, just combines them. So here's like the kind of the how they the differences between the representation. So you have the memref. So like Alex has mentioned, like memrefs, they're a logical view in that you see the exact it tells the dimensions that a certain memory that it's accessing should be instead of like a pointer. Um, and then, but what we need is something that explicitly has that data transfer. So here you can see this is the actual like memcopy ND with its source and destination that I've previously removed. So they keep they have the intermediate step because that's just their design for if they want to target like GPU, for example. So they have that intermediate kind of representation for it. So that's hardware agnostic. And then you change that to the AIE construct, which is their channel. And the difference with that is that channel actually says what thing you're going to communicate with. So here we're still representing it as like a variable percent channel, and that's left for the object FIFO to decide on. Yeah, so it's just like setting up for that. And yeah, for the put and get, that kind of touches on another thing where might have a synchronous memory transfer, or you can have like async versions. So that put and get is like, I guess it's kind of like a handshake in a way where it has to let each other know like when it's ready. Uh, yeah, there's probably more details to that I didn't really understand. So kind of another big big step that they actually do in AIR is the placement. So within a segment, you would have multiple herds, and for a single segment will have to be placed on the AIE tiles at once. So what they do is they pretty much do this in how like MLIR, you have essentially just tokens or tags. So what you do is you write down these information, you pass it down to the level that eventually does the actual, for example, like a routing or anything like that. So the placement is, I think, really simple. What they do is that the segment infers its own shape and size based on the herds inside it, and then they just assign herds in. Let's say like a herd has 4 cores in it. Then what they do is, I think what they do is like they just try to greedily like place it where you grow the X and Y proportionally. So if it is 4, it'll most likely end up as like a 2 by 2 somewhere on the AIE grid. Uh, like, and yeah, the way by greedily is just like you within a herd, there's going to be memory transfers. So the best way is probably to place them really close. So these will be adjacent, and yeah, like that's as far as their placement goes. Yeah, so for like this example is like you have there's more herds, but I only showed one. But the idea is just that it has a X and Y location that's some sort of coordinate, and that will be what AI uses to route uh later on. Yeah, so this is just kind of what I said before, is like you use like these tokens for synchronizations. And then once you pull out that data flow part from the computation, uh, you can schedule it with like by interleaving those. And how this connects to AIE is that for AIR, for the herd segment and launch kind of dialects that we saw, it's a pretty much a one-to-one mapping to an AIE. So that execute will be a core in AIE, and so on. So they clone this the now what is become an AIE MLIR file. They clone it. One for will be used for control code, which is the kind of the scheduling part, and then the other one will be used. They will take it and generate individual ELF files, where each ELF file is the computation instructions for a single core.
Inside that execute statement.
Yeah, for example, like that. So these will all be stored as a XCL bin, which is what I'm trying to represent with the sign. And then you would take a user written host code that has to kind of invoke certain kernels, for example, and then for your testing. So kind of what Hung and I still don't really understand is that instructions.txt. It's like another additional file that's generated. We think it's for between L3 communications, or it's like instructing it's like instructing L3 to pull certain data, but we're not sure on that yet. And then you can compile all these to get into an execution file, and then that's what actually runs.
And instructions.txt is linked with the core ELF or with XCL bin after everything's been compiled. So this is
Yes. So instruction text is separate from the XCL bin, and then these are loaded by the host code.
Oh, they're loaded. I see.
Yeah. So host code's the one that actually runs the or calls on these two. So yeah, there's probably still some mystery with this part.
So the interfaces to things like PyTorch, I assume they like the host code as well. Is that right?
Yeah. So for example, if you are, what we're showing is like, let's say I used AIR, and then how the host code is something that you would write as part of the AIR programming. So it would be together.
When they go from PyTorch, they go to the immediately fork the host code off, or they write it into the MLIR and a later stage pulls it out.
So if you really start with PyTorch, they have an end-to-end where in that PyTorch you can technically write that host code of testing in that same Python file.
Okay.
So that's if you want to go from all the way from the top. But I think the way they made AIR is that they're expecting like, let's, for example, like you're programming with this, like with CUDA, you would be programming with AIR, which you in that case you would be writing the host code in like AIR's Python APIs. Yeah. But if you only work with AIE, then you would have to write a separate host code file. And AIE would only be able to program the architecture part. Yeah. Yeah. That's it for at least the AIR section.
So just so I understand it, so the purpose of AIR is kind of just turning something that's more abstract, like a matmul, and turning it into what?
And so with the AIR is meant to be, so I guess you can think of it as like any tool. AIR will include that AIE flow, but it's made so that if you are like a user, you would just write that one, let's say Python file with I can technically write a matmul in Python and also test for correctness within that file. Or if you want to start even higher level, you can take a PyTorch matmul and also do testing there within that file. So it is an abstraction, but also combining the testing part. But but obviously you don't have that much control compared to AIE, where, for example, AIE programming with the iron tool is that I'm declaring tile locations, and then I'll be also be declaring which tiles I want communication between them. So obviously it doesn't translate to much use for like an application, but it's for a lower level of control.
Mhm.
So I guess the purpose of AIR is you want to do that same programming in an easier way. Yeah.
Mhm.
What do you recommend, if you go back a bit, what do you recommend is the best way to learn MLIR syntax? I've gone to their webpage and read up some of it. I understand it. I think at some level, but its syntax is complicated. And I think maybe I'm just not that
Yeah.
smart.
It's based on LLVM, so it's SSA and has to do some tricks to get around that
Well,
problem.
I can read LLVM stuff reasonably well, but I find MLIR is more abstract than that. So just read their website repeatedly and read the code, or what? Does
To be
anybody have a
honest,
better solution to that?
they have tutorials online, MLIR tutorials, and they walk you through how to go through different levels of abstraction. My recommendation for learning MLIR is take a matmul in linalg and try lowering it to SCF and see how it looks. Then try lowering it to CF and see how it looks now. Then lower it from CF to LLVM and then see how it looks now. And what you're going to notice is why things are going down one step at a time. That's what I recommend. It's a great way of just kind of figuring out why we have these dialects.
Okay. Is there a tutorial you recommend that does that?
I wish there was. Let me see.
I'll search.
Using MLIR OBT has to be here. Huh. I actually don't know why they don't have that.
Cool.
Yeah.
Thanks, James. I have to run to another meeting, but
Yeah.
I think this will be the first of many times going
I
through the
know
syntax of this.
it's really confusing.
All right, I'm going to stop the recording.